Let's say we want to make an amplifier with a certain bandwidth. What is then the requirement for the operational amplifier that we put in for example, its gain bandwidth product? We need to have a clear procedure for that. We are going to make a model of the operational amplifier, and that is what I did, I think 2 lectures ago. We selected an operational amplifier and modeled its dynamic behavior with a controlled source, and in which there is the pole and probably input impedances and output impedance of the operational amplifier. So if we do a model with a DC gain and a single pole, what we did with the transimpedance integrator, the example, then we can model the voltage gain of the operational amplifier as the DC gain divided by 1 plus S times the DC gain divided by 2 pi, its gain bandwidth product. Unfortunately, this is often called the open loop gain. Well, loop gain is not a property of an amplifier, of an operational amplifier, because it's the controller and you can make any loop with it. So it's like a little bit a nonsense word. So we call it the gain of the operational amplifier. And this is the DC gain of the operational amplifier. But in data sheets, you often find DC open loop gain. Well, if there's no loop, what is then the loop gain? So the differential mode and common mode input capacitances, I have shown you in this previous lecture how you can find them in a data sheet and how you should model them, and the output resistance. Then, if there are any numeric values that if you initially, for example, for the accuracy or so, you already know I want to have a DC gain of the Opamp more than so and so, you can put in this number if you want. So anything that is to be designed to keep it symbolically in equations, and then we are going to derive an expression for the loop gain, mixed symbolic numeric, so there can be the source resistance or source impedance in it, and the load resistance or load impedance, and we know them already because they are usually the starting point of the design. And don't keep them in the equation like symbolically, because then you get an equation with 25 parameters at the end or more, and you cannot read it anymore. It doesn't tell you anything for designing. So minimize, make your model as small as possible so that it tells you what you need. Remember, all models are wrong, but some are useful. And models should be as simple as possible, but not simpler. Then we have Box and Einstein together. So then we are going to determine the loop gain pulse product and its order from this expression. There are tools in SlideCap to help you with this. And we solve the gain bandwidth product. If you put the gain bandwidth, of course, as a variable in the equation, we solve it from this nth order loop gain pulse product minus the desired bandwidth to the power of n equals 0. And then you get the solution for your gain bandwidth product. Showstopper values for the gain bandwidth product. Let's say, of course, there can be other parameters of the operational amplifier that contribute to the loop gain pulse product. And usually the gain bandwidth product is the one that makes it larger, but parasitic capacitances like input capacitance makes that you need, if there is it creates extra pulse. So then you need maybe a larger gain bandwidth product to achieve with that op-amp the same characteristics. So a showstopper value, an absolute minimum gain bandwidth product that you would need, can be found if you make all the other things 0. So if you make input capacitance 0, output resistance 0, then you say, well, I need at least to have an operational amplifier with so and so much bandwidth. And later on, you can add other things and see what is then the impact. So do it step by step, then you keep track of your design. And there is an example in the book